Okay, it looks like it's recording. So it's my pleasure to welcome Sam Miller from University of California, Santa Cruz. He'll talk to us today about endotrivial complexes.
Thanks, Scott. I'd like to thank Dan and the organizers again for having me. This is really exciting. It's my first time speaking at a different school seminar. Yeah, let's begin. First, let's start with some notation conventions. So for this talk, G is a finite group. Little k will be, getting ahead of myself. P is a prime. And little k is a field of characteristic P. Note that we're not making any assumptions about k being large enough. We're just taking it to be an arbitrary field of characteristic P. Modules are finitely generated. And another one that is a little less common, chain complexes will be bounded. And a few others. Sorry, my pen tip fell out. We'll denote by SPG set of P subgroups of G, and Sylow PG be the set of Sylows, Sylow P subgroups of G. And finally, just use this to denote K dual of a KG module. All right. And so it feels a little silly to say all this motivation because I'm talking to some of the world's foremost experts about this topic, but we can say that the KG module M is, we'll say, endotrivial if the M dual tensor over Km, which is isomorphic to end K of M, is isomorphic to just the trivial module plus P with a P a projective KG module. And there's a couple more generalized notions as well. We have endopermutation, if M dual tensor over K M, I'll just say, is a permutation KG module. In other words, it's isomorphic to Kx, where X is a G set. And finally, we have a slightly wider notion that's a little less common, endo P permutation. If M dual tensor M is a direct summand of a permutation module. And we have these three classes of modules. I'll focus on endotrivial since, well, it's in the title. And the goal here is to classify, or a goal is to classify these modules. And what do I mean by that? Well, I mean we can describe, we want to describe and find generators of, so I'll stick to endotrivial modules here, TKG, or just TG, which is the set of isomorphism classes of endotrivial modules in the stable module category of Kg, where M is endotrivial. And similarly for endopermutation, endop permutation, specifically capped endopermutation, but I don't want to get into that. And so much work has been done, by some of which has been done by some of the audience members here. And so, for example, we have some theorems. I'm saying these to motivate some of the things that I will be talking about later. So some facts. TK of G is finitely generated. And this goes back to Hooge in 1990, or I believe, so I may be getting this wrong, but I believe this is just for P groups. And then the first time I've seen this actually mentioned for non-P groups was due to Carlson, Manza, and Nakano in 06, but this may have been known earlier. But this is at least where I've seen the first mention of this.
Dan says he thinks it was known earlier.
Ah, okay.
I think John also had other proofs.
And John might have had other proofs of this.
Or earlier by thank you. And so TK of G was classified, completely described for P groups. And this is goes back to a couple of papers by Carlson and Tevena. I think ranging from 2000 to 04. Again, I might be wrong there. And then it's been classified as well for other groups, but not all of them. This is still an ongoing. This is ongoing still. Described or just other groups. And this is just goes to the work of many. And so the idea here is that, or one of the reasons we study these is that endotrivial modules are what we can say the invertible objects, multiplicatively invertible in ST mod KG. And so one question we can ask is, what might the analog be for chain complexes? And there's not really, perhaps there's not one correct answer here, but well, I've cooked up a few. And so unfortunately to begin, before we can begin though, we need to cover a few preliminaries.
Dan has a comment.
Yeah.
So the endotrivial group is finitely generated feeling. So the torsion-free part is not very hard to compute, but it's the torsion part.
I'm sorry, I couldn't quite hear that.
Yeah, so Dan is saying that the torsion part is the hard part to compute.
Right.
The torsion-free part is
The torsion-free part is not hard.
rank torsion.
The torsion-free part usually comes from relative syzygies, right?
Yeah, and it also uses just elementary feeling. So if you know conjugacy across the long.
Couldn't quite hear that one either, but
Conjugacy class.
Yep. The conjugacy classes of elementary abelians allows you to compute the rank.
Ah, right. Restriction to the elementary abelians. Right.
Okay.
Yeah. Okay. In the interest of time, so I'll move on. So we're not just going to be studying arbitrary endotrivial complexes, actually. We're restricting to a slightly friendlier class. And this will be for a number of reasons, which I'll describe later. To do this, I first need to describe what p-permutation modules are. And I already mentioned the name, but we can talk about them in a little more detail. The KG module M is p-permutation if and only if the restriction of P to of G to a P subgroup P is in fact permutation for all P subgroups. And we denote subcategory of KG mod with P permutation objects by KG triv. And why triv? Well, I'll get to that in a bit. So you can say this is A. And B, I'll just review relative projectivity for if anyone's unfamiliar with this. AKG module M is H projective if M is a summand, I'm using this to denote direct summand, is a summand of some KH module N induced from H to G. And H is subgroup of G. And we say if M is indecomposable, a vertex source pair, forgot to note these, is a tuple, say PS, with P a subgroup of G such that P is minimal to, or minimal with the property, or with respect to the property of H projectivity for M. Sorry, that's a little unclear. And S in KP mod is such that M divides from P to G of S. And I write P because it, in fact, vertices are always P subgroups. And so one theorem we have that characterizes P permutation modules that M is P permutation if and only if M is a summand of a permutation module if and only if every indecomposable summand of M has trivial source. which kind of just follows from the second condition because all transitive permutation modules are of the form int GHK for some H. And so these sort of are a slight generalization of permutation modules that we're interested in studying, and these do show up quite frequently in the study of modular representation theory. So unfortunately, we need to go through a few more definitions before I can get to the good stuff. This is definition 1. So we'll have a pair of subgroups, K contained in H, contained in G, trace map, which we'll denote by TR, going from K to H. And so we always have a map from the H fixed points to the K fixed points of M, just sort of given by, well, inclusion, because if it's H fixed, then it's K fixed. But this goes in the opposite direction. This will send an element, M, to a sum where we take a set of coset representatives of H over K, and then just multiply it by G and sum those. And this, in fact, is well defined. Check that. In the Brauer construction, well, this is integral for the study of p-permutation modules and shows up in many places for local to global modular representation theory. Brauer construction, sometimes also called the Brauer quotient. And this is defined as, we'll denote this as M of P. And what we do is we first take M, we take the P fixed points, and then we divide out, or we mod out by all trace map sums from all subgroups that are strictly contained in P. So we just mod out by all trace maps, essentially. And I write P here, you can define it for any subgroup, but it turns out that this is uninteresting. It's just 0 when P is not a P subgroup. So we only really consider the Brauer construction for P subgroups. And so M of P has a natural KNGP module structure, and it's P fixed. So therefore, it's a KNGP mod P module. So this is a KNGP module, which is P fixed, hence a KNGP mod P module. This also induces a functor, denoted by dash P. Say it goes from KG mod to KNGP mod P mod. But it also preserved P permutation. So it can also be considered a functor from KG triv to KNGP mod P triv. And in fact, this is oh, sorry, I'm getting a little ahead of myself again. So this can be seen as sort of a generalization of taking the fixed points of a G set. So if we have a P subgroup, P and SPG, and X a G set, then we have a natural isomorphism, the KG module KX. If we take the Brauer construction there, this is just the same thing as first taking the P fixed points of the G set and then K-linearizing. And this is a natural isomorphism, canonical isomorphism. And in fact, this is the closest that we can get to a functor, which is analogous to taking, an additive functor in particular, that is analogous to taking fixed points of a G set. And unfortunately, I don't have the time to go through this. I was planning on going through it. So I thought the argument's quite nifty, but well, in the interest of time, I think I should move on. And so the last thing that I want to mention is that the Brauer construction is very well behaved with p-permutation modules. Just like how taking fixed points is very well behaved and quite interesting when studying G sets. So I'll just rattle off a few propositions. So let M be a p-permutation module. Then the following things hold. The Brauer construction naturally commutes with the tensor product. This is a big one. It's also additive, but just admitting that, it's pretty clear. So if M is indecomposable, with a vertex P, say vertex Q, M of P is not equal to 0 if and only if P is contained in Q. So in other words, what it does, or what the Brauer construction can do, is it detects vertices and it kills off anything whose vertex is essentially too small. We have a nice little computation formula. If we want to conjugate by a group element G, create a module that way, this is the same thing as just conjugating by P, the inside. Another thing is that, this is also natural. Another fact that we have is that this is also that the Brauer construction commutes with duals. And finally, the Brauer construction can be used to essentially detect when things are split surjective or split injective. And the idea here is that you can take a look at a map, apply the Brauer construction to it everywhere, and if it remained surjective or remained injective after applying the Brauer construction everywhere, then in fact your map was split surjective or split injective to begin. So I'll just write it in brief as F from N to N, where N is also p-permutation, is split surjective and follows dually for injective, if and only if for all P subgroups, P, F of P from M of P to NP is surjective. Okay. This is all that I have to say just for the preliminaries, and I should check to see if there's any questions before I continue.
I think we're good.
All right. Now we can get to the fun stuff. Endotrivial complexes. So what are these? Let me tell you. Bounded chain complex, C, which I'll specify is actually in kg triv. So it consists of p-permutation modules, is an endotrivial chain complex or just endotrivial for short, if, well, you can kind of guess what's going to happen here. C star, considered over K, C, is in this case homotopy equivalent to K in degree 0. So this just sort of means 0 to K to 0. In other words, is isomorphic to K plus say D, where D is a contractible chain complex. And so why do we want e-permutation? Well, one very important motivating reason for me is that these endotrivial chain complexes, in fact, induce splendid Rickard complexes of the group algebra KG. I don't want to say too much about this, but it is a motivation. So if we take C, regard it as a K delta G, where delta G is the diagonal embedding of G into the group G cross G, and then we induce it up from delta G to G cross G, then regard this as a complex of bimodules. This is a splendid Rickard complex for KG and KG. And this is actually a motivating reason for me to study these, because my original dissertation question involved studying splendid Rickard complexes and the relationship to p permutation equivalences. If you don't know what those are, don't worry, I won't talk too much about them. However, my focus seems to have just shifted to this point to endotrivial complexes. And another reason, also, we just have some grasp on them. Whereas I've tried studying endotrivial complexes without this assumption that all the terms are p permutation, and I can't make heads or tails of what's going to happen. Paul Ballmer recently has a paper describing p permutation resolutions, and the fact that every KG module has a finite p permutation resolution. Unfortunately, I haven't been able to, I was hoping that I would be able to use this somehow, but I haven't found a way just yet. So let's just note real quick that the Kunith formula implies that C has non-zero homology. Oh yeah, the indices are decreasing for my chain complexes in exactly 1 degree. With that homology having k dimension 1. This isn't sufficient, of course, but it will be a key property. So just as a basic result of the multiplicity of the Brauer construction, we have that for any p subgroup, Cp is, sorry, I should specify, C is an endotrivial complex. Cp then is an endotrivial K NGP mod P complex. So given any endotrivial KG complex, we can sort of induce these local endotrivial complexes, local at the normalizer level. And in fact, new page, using this, we get a nice detection theorem for when we have if we have some complex and we want to know if it's endotrivial, the Brauer construction can help us determine that. So just write detection theorem. C is an endotrivial KG complex if and only if, for all P subgroups, P and SPG, Cp has this homology property. Has a non-trivial homology in exactly, I guess I should say non-zero. Non-zero homology in exactly 1 degree. And it has k-dimension 1. The homology is k-dimension 1. So the forward direction is quite clear from what we've seen. And the reverse direction, on the other hand, it happens only because of properties of p-permutation and the Brauer construction, the nice interactions that they have. And so this is also this idea was communicated to me by my advisor, Robert Volge. And so with this, we can have some notation. So we can write HC. Now I call this the H mark of C, or equals the index I with the unique index with HI of C being non-zero. And we'll write capital HC, just sort of an abusive notation, by HC C. And I like to call this the H mark of C. And more generally, I also say HCP, noting that CP is also endotrivial. This is the H mark of C at P. And so this is analogous to the marks if you study the Burnside ring, which is the Grothendieck group of G set, then there's the Mark homomorphism, which studies the size of the fixed points. And it turns out that the Mark homomorphism is injective. All of the marks make up the structural properties of your virtual G set. So now the question we can ask is, how much do these H marks determine the structure of C? So to do that, well, what exactly do I mean determine the structure? So we can define the group of endotrivial complexes and ask how many different group elements have the same H marks. So we'll do curly EKG, sort of similar to what we do with endotrivial modules. This is the group of endotrivial complexes up to isomorphism in the bounded homotopy category of KG triv, such that C is endotrivial. And just note that this is a group under the multiplication induced by the tensor product. And here is the big theorem. And I have to especially thank Dan for this theorem, because about half a year ago, I was giving a talk and he asked me a question about whether this group is finitely generated. And at the time, I hadn't even thought about it. And thinking about that question led me to essentially cooking up this theorem while I was driving back home from the conference, which is probably not a very safe thing to do, but it was an interesting question. We have a group homomorphism from EKG into a product of of a bunch of groups of integers, additive, indexed by the P subgroups. And this is actually G fixed, where G sort of acts by conjugation on your indexing set. And what do? Well, we take a representative of an endotrivial complex, and then we just take its H mark everywhere at all P subgroups. This is sort of analogous to what we do for the regular Mark homomorphism. I should say it's this. We call this epsilon. At least I'm calling it epsilon for now until I come up with a better name for it. And what is the kernel of epsilon? Well, thanks to the properties of p-permutation modules in the Brauer construction, we can compute that it is in fact the endotrivial complexes which are just given by one-dimensional Kg modules concentrated in degree 0. Well, at least up to homotopy, where omega is just a group homomorphism from G to K star. And so what does this tell us? Well, this is finitely generated, and this is certainly finitely generated. So in particular, EKG is finitely generated. Abelian. With rank bounded by the number of conjugacy classes of P subgroups of G. And this is actually attained. For example, in the cyclic case, we can attain this. But in general, for most of the groups that I've actually computed this group for, it's not attained. And I feel like there should be a better way, perhaps also using restriction to elementary abelian subgroups to determine what this rank is more explicitly. But we're not there just yet. And so moreover, we also have that any two endotrivial complexes with the same H marks are homotopy equivalent up to a twist just tensoring by a one-dimensional module, by a one-dimensional representation. So this was the first big result that we had. Before we move on, I should ask, are there any questions about this?
I don't think so. Oh,
All
Dan.
right.
So how extensive are your calculations? You said you can do it for the other example.
You'll have to repeat that.
Can you do examples that are not necessarily cyclic groups? He's wondering how extensive your calculations are.
Yes, we'll get there. So the groups that I've done it for are all abelian groups, and then dihedral groups, semi-dihedral groups, quaternion groups, and those.
Thank
And
you.
then it seems like in general, explicitly computing these does not seem easy, and I'll describe why that is later on. But we've at least worked through those. Oh, and additionally, any just group that has any of the groups that I just listed off as Sylow subgroups. So actually, that's a decent number. So section 3, decomposition. And this actually describes how we do some of these computations. So for this, let's let N be a normal subgroup in G. So we can always deflate, in a sense, by applying the Brauer construction we'll first restrict and then go to a quotient subgroup, but we can go in the opposite direction as well. We can always go from G mod N to G by inflation. And this induces an injective group homomorphism from EKG mod n to EKG. And now I'm going to go on a brief tangent. For those of you who have heard of biset functors before, EK dash is not a biset functor, unfortunately. Since we do not have an induction functor. We can't go from EKH to EKG where H is a subgroup. Unfortunately, so one would think that because we're working in a multiplicative setting, tensor reduction should work. But unfortunately, no, tensor induction fails quite miserably. And the key issue here is that it fails to preserve homotopy equivalence. And just, it doesn't even preserve contractibility. In fact, in the Paul Ballmer paper I was talking about earlier, the fact that tensor induction fails to preserve contractibility plays a key role in his main theorem. But we do have inflation and deflation. And deflation is the Brauer construction. And so modifying techniques of Serge Bouc, which he used in his study of biset functors, which were quite crucial, I believe, for various parts of classifying endotrivial modules, but more generally the Dade group. We obtain the following definition. So we'll denote this by a partial EKG, and this will be a subgroup of EKG, which will be the intersection of all kernels of normal P subgroups, except for one. We'll take the kernel of the map that's induced by the Brauer construction. And this is what we call the faithful constituent. Of EKG. And one can think of this as sort of being the group that consists of endotrivial complexes, which are not induced from smaller quotient groups. And I'll make this more precise in the following way, with the following theorem. We have a decomposition of EKG into all of its faithful constituents, but the faithful constituents coming from quotient groups as well. And so this will run over all normal P subgroups, where P is in SPG. And so therefore, if we want to compute EKG, if we've already computed it for all the quotient groups, then really all we have to do is just compute what this is just for the faithful constituent. And we can also say what this map explicitly is. I'll say it in the reverse direction. The forward direction is kind of ugly and involves the Mobius function over the post set of normal P subgroups. So we'll just send all of these. First, we'll take this tuple of local endotrivial complexes. We'll first inflate them from G mod P to G. And then we'll just tensor all of them together. So essentially, to determine EKG, it suffices then to just determine this faithful constituent. And moreover, because we know well, if we're looking at the kernel of all of these Brauer constructions, then we know then that the only place that a faithful endotrivial complex can have non-zero H marks are at the smallest P subgroups, the ones that don't contain any normal P subgroups other than just the trivial. And so we know exactly, essentially, what these complexes have to look like. And we know this from the following theorem as well, which is a bit technical. And then the proof is also very technical. So let's see an endotrivial complex. So this is a restatement of a more general theorem that I proved, but specifically for endotrivial complexes. And let's let curly X be a subset of SPG. Let it be a sub-poset closed under conjugacy, under G conjugacy and subgroups. It must satisfy the following property, such that for all P which are not contained in X, HCP is equal to HCS, where S is a Sylow P subgroup, any Sylow P subgroup. Then the following holds. C HCS as a, so this is the HCS index of C, as a unique indecomposable summand with K dimension 1 and vertex S and all other summands have vertices in X. And then what about all the other terms in C? When I is not equal to HCS, CI is X projected. What this means is that each term in CI has, or each indecomposable summand of the module CI has vertex that's contained in X. And in particular, this holds for any faithful complex when X is the set of P subgroups containing no proper normal subgroup of G. So just only one. And so what this tells us then is that all of the vertices that occur in all of the indecomposable modules in our endotrivial complex are sufficiently small, like close to projective, if not projective, with the exception of exactly one vertex. Oh, sorry, there's one thing that I forgot to mention. This should be assumed to be indecomposable. And like in the endotrivial module setting, if you have an endotrivial complex, it turns out that it has a unique, non-contractible, indecomposable summand, and that summand is also endotrivial. Otherwise, you can say that this all holds up to homotopy. So if you just remove all the contractible summands, then the statement holds without the indecomposable statement. And so this tells us that if we have a faithful complex, well, it can only have so many different types of terms in it. The proof of this is pretty long and technical. It involves first generalizing a theorem of Serge-Bouc, which also relates to the Brauer construction and permutation modules, and tells you, the original theorem tells you precisely when your chain complex up to homotopy only has permutation modules, and we generalize this just for relative projectivity. There's some homological algebra arguments in there. Okay, with this decomposition, we can determine the partial EKG, then EKG for the following classes of groups, and probably more as well, almost certainly more as well. Abelian groups, dihedral two groups, quaternion two groups. The quaternion one essentially follows from dihedral. And the most interesting one, I think, is semi-dihedral one. And for all of these, it turns out that the Z rank of partial EKG is equal to 1. There's always one faithful endotrivial complex, which for it and all of its duals generates the rest of the group. And in fact, this one, the construction of this one hinges on the existence of torsion endotrivial modules. The basic construction is you take the corresponding chain complex for the unique torsion endotrivial module for a semi-dihedral two group, and then you square it, and then you chunk on a few more projective modules. And so it has length 5. Oh, plus any group with Sylow P subgroup, the as above. And this is actually quite new. This is the last thing that I want to talk about today. We started a little late, so is it okay if I go for a few more minutes?
Yeah, that's fine.
Great. Okay, for
Dan
a
has,
fifth section as well, but we're not going to get
Dan
there
has a
today.
quick question.
Oh, yeah.
So does this, so you have this theorem about this zero rank one situation. Does that depend on, like, can you state something in terms of the size of elementary dealing, the P rank is bigger than the can you conclude that the rank of EKG is one?
Can you repeat that?
If the P rank of the group is like bigger than or equal to 3, then you conclude like the rank Z of EKG is 1.
Scott, I think you have to repeat that. I can't quite hear Dan.
You want to just come next to
Oh yeah.
Sorry, if you take the P rank of an elementary abelian, and if it's bigger than or equal to 3, for example, can you conclude that the rank Z of EKG is 1? So this is like the endotrivial group case.
Hmm. Yeah, maybe the same technique will work here to determine the explicit ranks.
Right. So it's sort of generic as long as the P rank is big enough.
Mm-hmm.
Okay. All right, one minute. Okay, good.
Thank you. So the last thing I want to talk about is restriction to Sylows. Or, well, really, any subgroup that contains a Sylow subgroup. Try to make this quick. Not running out of time. So goal is determine the image of the map restriction G to H from EKG. I hope you can't hear what's going on in the room next to me. It's quite loud. Where say that H lives between S and G for some Sylow subgroup. And so let's note that for any endotrivial complex, it follows by properties of the Brauer construction that HCGP is equal to the H mark at P is equal to the H mark at any conjugate of P, essentially. And so therefore, this tells us that something about the elements of the image. So for any C in the image of restriction, the same holds. So we say an endotrivial H complex C is right curly F stable, sort of for fusion stable. If H, the H mark at P is equal to the H mark of any G conjugate of P for all P which are subgroups, P subgroups of H, and G in G, satisfying that P conjugated by G is also contained in H, because otherwise the statement makes sense. And so to note the subgroup of F stable elements of EKH just by EKH superscript F. And the main theorem, and this is new, so I have a preprint up on arXiv, which contains much of this stuff as well as many more things I don't have the time to get to. This is fairly new though, and I'm hoping that it'll be in the next preprint that I'll have in a month or two or so. If we consider restriction as a map from EKG, so we know the image must be contained in EKGF. This is actually an isomorphism. Oh, sorry, no, that's not quite true. It is surjective. However, it is an isomorphism if H contains the normalizer of S. It is an isomorphism And in fact, with the inverse induced by the green correspondence, for complexes that John and collaborators has studied. And there's two key elements to the proof of this. The first one is that endotrivial complexes, so I'm going to say some words, some of them might be unfamiliar. Endotrivial complexes are just shifted versions of endosplit p permutation resolutions, which were defined by Rickard in his 96 paper, which also introduced splendid Rickard complexes. These are endosplit p permutation resolutions of one-dimensional KG modules. And that's another way that you can think of these. So that's the first step. He has a specific theorem that shows that if you have an endosplit p permutation resolution of some KG module, then it contains summands with all of the summands of the module that it's an endosplit p permutation resolution for. There are summands in the endosplit p permutation resolution of those summands. That's a word salad. And the second step is that we derive a Mackey formula for describing how induction and the Brauer construction commute. And to what I've seen, this has not been done before. It's been done partially, but this is the most complete version that I've noticed. But I could, of course, be missing some paper somewhere. And what this does is it shows that induction of fusion stable complexes, well, we have a grasp on. Specifically, we know that if we have a fusion stable complex and we induce it, then the resulting thing, well, it won't be endotrivial, but it will at least have homology concentrated in degree 0, and it will split. So therefore, it'll be homotopy equivalent to something with homology in degree 0. And using these two things together, we can deduce this form. And I believe that's all the time that I have now. So I think I'll end here.
Thank you, speaker.
Thank you all for having me.
So any questions for Sam? It doesn't look like so. Let's thank Sam again. Yep. Yep. Thank you.
Yeah, thank you for having me.